Well, now we're going to look at the second possible proof of theorem 2.4, number 1. This time, instead of using a delta epsilon proof, we're going to use sequences instead. So remember what that means. If I want to show that the limit exists, that the limit as x goes to x naught of this function is L plus m, I just have to show that every convergent sequence, every sequence xn that converges to x naught, and I guess to be precise here, I need a sequence of numbers in the domain that are not equal to x naught, but converge to x naught. Every such sequence, f plus g of that sequence xn, will converge to L plus m. And we don't have to show all infinitely many of them. What we'll do is we'll just take one arbitrary sequence and show that it converges to capital L plus capital M. Since a sequence was chosen arbitrarily, that means every possible such sequence would converge to L plus M. So we need to start off with a sequence. Let's let xn, and going from 1 to infinity, be a sequence whose numbers are made up from the domain capital D, but not including x naught. So let's make it a sequence in D minus x naught that converges or has its limit at x naught. So we've got a sequence of numbers xn that converges to x naught, and none of those numbers is equal to x naught. Well, to complete the proof, we will simply show that I don't know, I'm going to write that. I'll write it like that. F plus g of xn, which this is now a sequence. And I'm going to rewrite it in the way that I like it. F of xn plus g of xn converges to L plus m. That's all we have to do. Well, this turns out, based upon theorems that we already know, this is going to be fairly simple, fairly straightforward. Okay. By theorem 2.1, we know that f of xn, that sequence, converges to L. Why is that if we were writing the justification? Because of this. Theorem 2.1 tells us that. If we know that f of x converges to L as x goes to x naught, that means that every single sequence of xn's that converges to x naught will have f of xn converging to L. And likewise for the second one, we've got the sequence of f of x g of xn's converging to m. So that's by theorem 2.1. And to finish this off, we go back to nothing but sequences. We're going back to the last chapter. Therefore, and I'll put in parentheses by theorem 1.8, and go back and look at that. F of xn plus g of xn, taken as a sequence, n equals 1 to infinity, converges to L plus m. And that's the end of the proof. That was actually, I don't know how much more simple it was, but it was definitely shorter than the delta epsilon proof, converting us to a problem using sequences.